Trigonometric functions are extremely common and important. You should already know a bit about sine and cosine. Let's review perhaps the most important of the trigonometric identities. That is, cosine squared plus sine squared equals 1. There are several ways to interpret this. You've seen the interpretation involving a right triangle with hypotenuse equal to 1 and with angle set to theta. Then, in this case, the sine of theta is the length of the opposite edge to theta, and the cosine of theta is the length of the adjacent edge. If we think of those as x and y coordinates respectively, then we see that there's a relationship between this trigonometric identity and the equation for the circle x squared plus y squared equals 1. And indeed, if we think of what happens when we move a point along a unit circle, rotating it by an angle theta from the positive x-axis, then the x and y coordinates of that point on the unit circle are precisely the cosine and the sine, respectively. Other trigonometric functions are common and important. I'm sure you recall the tangent as the ratio of the sine to the cosine function, and its reciprocal, the cotangent function. One can also take reciprocals of cosine, obtaining the secant function, and of sine, obtaining the cosecant function, respectively. Now, all of these that involve ratios wind up having vertical asymptotes in their graphs, that is, places where the function is undefined when the denominator goes to 0. The inverse of the trigonometric functions are very useful, but somewhat treacherous. You've got to be careful. Some students like to write the inverse of sine as sine with a -1 superscript. That can lead to some confusion, thinking that it is the cosecant or the reciprocal of sine. That is unfortunate notation, and I encourage you to use instead arc sine to denote the inverse of the sine function. The arc sine is that function which, when composed with sine, gives you the identity back. One of the things that you'll note about both the arc sine and the arc cosine is that they have a restricted domain. The domain must be the closed interval from -1 to 1, because, of course, sine and cosine can only take values in that interval. In contrast to this, the arctangent function does have an infinite domain. Its range, however, is limited between -π/2 and π/2. These are all functions that you're going to want to be familiar with for moving forward in calculus. The last class of functions that is of critical importance are the exponential functions. These are functions of the form e to the x, e to the x being the canonical example of an exponential function. Its inverse is the logarithm, or more precisely, the natural logarithm, ln of x. You've seen these functions before. You know, because they're inverses, that their graphs have this symmetry about the diagonal. So, for example, if e to the 0 is 1, as it must be, then log of 1 must be equal to 0, certainly. The question that is often unanswered in pre-calculus or even elementary calculus courses is, what is e, and why is it so important in this exponential function? Well, one could say that e is that value whose logarithm is equal to 1. But since we've defined the natural logarithm in terms of base e, that's a bit of circular reasoning. How do we reason about e? Well, certainly e is a number. It is a particular location on the real number line. It has a decimal expansion, but being irrational, it is a little bit hard to remember all of it. That doesn't really answer the question of what is e. Why is it so important? Before we get to the answer to that, let's review some of the algebraic properties associated with the exponential function. I hope you remember that e to the x times e to the y is e to the x plus y, the exponents add, and e to the x raised to the y power is e to the x times y. In your prior exposure to calculus, I'm sure that you've seen some of the differential and integral properties of this function. E to the x has this wonderful property that it is its own derivative, and, of course, that it is its own integral, at least up to a constant. These facts are easy to remember, but maybe not so easy to fully comprehend. There is one last ingredient that we're going to need before we go deep into exploring what e to the x means. This is something called Euler's formula. This is simple looking. It states that e to the I times x equals cosine of x plus I times sine of x. This is a wonderful formula. Whatever it means. What does it mean? What is this I that is in here? I am sure that you've seen before the notation for the square root of -1 for the primal imaginary number I. That is what is meant in Euler's formula. It has the property, of course, that I squared is equal to -1. Well, this is a formula. It's a true statement. But what does it mean? Well, that is the subject for our next lesson.
And so we end with a mystery about the exponential function and what it means to exponentiate something that is not a real number. In our next lesson, we'll resolve this mystery, in part, by contemplating what the exponential function is.